Actually, someone is asking to get in, no. Yes, we can allow them to get in, Camila. Both of them are from the team. We have to include them, their name on the list, or Camila and Erica. Okay. Good morning for everyone. Today, we have a pleasure to have here in the CINE Talks the André Navarro de Miranda. He obtained his Ph.D. supervised by Professor Gustavo Dolbeck at the UNICAMP, working on the lithium-ion batteries. And today, he, of course, then means that he's a very good health. Sorry. He has very good expertise on the lithium-ion batteries, and today he's going to provide an introduction for us because it's a very important topic, because those batteries allowed to enhance the density energy. It means it has better efficiency for energy storage. Okay, André we are very happy to have you today. Once I close my camera, and I'll count 1, 2, 3, you are ready to go. Okay, thanks.
Thank you, Juarez, for the introduction. Well, my name is André. I'm part of the lithium-oxygen, lithium-ion batteries here in CINE. I'll give you guys a look about these batteries, to understand a little bit why should we research the lithium-ion batteries, how do they work. I will show you some experimental results, and I'll talk a little bit about the next steps that we are doing here at UNICAMP. So yes, the first motivation to research lithium-ion batteries is about electrification. So if you see here in the chart, we talking about electric vehicles. We start with lead-acid batteries, and then we are going up close to gasoline, talking about theoretical energy and practical specific energy. And lithium-oxygen batteries are somewhere near here. So they are really near gasoline, so should be a good possibility in the future. Here is a study from National Platform for Electromobility in Germany, and they see lithium-ion batteries as the next kind of batteries that are going to be around near 2030. So it's a good technology to be studied. Another motivation to research lithium oxygen batteries, it's about stationary energy storage. So when we talk about solar energy or wind power, we are talking about intermittent energy sources. So for example, for solar power, of course, we have a peak of energy generation near 12 p.m. and we want to store this energy. And a good way to do that is to have like these containers here that could have lithium oxygen batteries to store this energy and then to release them in the night when another sources of energy are used, such as gas or carbon. Well, so here's attendance. We see about publications and patents in lithium-ion batteries. So we start with this curve here, and then we see a real boom of number of publications and patents. We see the same behavior for lithium-ion batteries. We still are starting to research this kind of technology, but we see a nice tendency to go up. So I think we have people from different backgrounds here. So I will explain a little bit how batteries work. So this is a traditional lithium-ion battery. We have a cathode, separator, and then anode. As cathode, we usually have some kind of transition metal oxide, such as cobalt or manganese or nickel or LFP, lithium phosphate, iron. And as anode, we usually have a source of carbon. So for example, here you have graphite with lithium. And then during charge and discharge process, you have lithium migrating from the anode to the cathode, and then to the cathode to the anode in the charge and discharge process. Well, how can we improve lithium-ion batteries, thinking about the next 10 years? Just checking, I'm not seeing you guys. You guys hear me well and see me well?
Yes.
Thank you. So how can we improve lithium-ion batteries? So first thing, we can substitute the carbon matrix for methyl lithium. This increase the capacity in terms of volume and area. So this is very good for the battery. And you have another possibility. So someone think, well, let's change this cathode. Let's not use a metal oxide, transition metal oxide. Let's use a carbon matrix. Then we open this battery to the air, to the atmosphere, and then we capture oxygen. In this process, we can form lithium peroxide. So this is not an intercalation process. This is what happens in the lithium ion batteries. This is a formation of a new product. And in this process, you have a lot of energy stored in the battery. So in the discharge process, we have formation of lithium peroxide. And then in the charge process, when we connect the energy, we have the composition of the lithium peroxide. So this is how lithium-ion batteries or lithium-oxygen batteries work. So this is one of the first ideas that we have. So for example, for the electric vehicle, the idea was to capture air, oxygen from the atmosphere, and use this oxygen to the reaction. Today we see this is not very practical. We prefer to pressurize the cell with oxygen. It works better this way, but we're still researching how to do that. So how do they work? So we have the reaction of lithium, metal lithium, with oxygen, forming lithium peroxide. For this reaction to happen, in the cathode, we need a triple phase. This is a big challenge. We cannot work with the battery with a lot of electrolyte because we need this triple phase to have ions from lithium. We need to have oxygen from the atmosphere. And then we need to have the carbon matrix that will transmit the electrons. So we need this triple phase for this reaction to happen. We cannot have water because we are working with metal lithium. Lithium metallic is really reactive to water, so we cannot have water in the system. We also cannot have CO2 in the system because there is a tendency to form lithium carbonate that's really stable and does not decompose. So it's another problem. We also cannot work with high currents because it tends to formate carbon lithium CO3. So it's really dangerous to the battery as well. So these are some challenges that we have to overcome to use this technology. So this is 2013, one of the first results in lithium oxygen batteries about 10 years ago. So this is how this battery works. The potential, it's about 3 volts in these batteries. And then when we discharge the battery, we have a kind of plateau here. That's the plateau when we are forming the lithium peroxide. Then when the cathode is full of lithium peroxide, we stop the discharge process and then we recharge the battery. Here we can see a big overpotential for the charge process. So the equilibrium voltage here is about 3 volts, and for charge you use 4.5 volts. So it's a lot of distance between the potential of equilibrium and then the charge potential. Then in this process, we use catalysts to decrease this overpotential. The first catalyst studied in the literature was gold and platinum, but they are very expensive. Then after that, we have like manganese as catalyst as well. So manganese is a transition metal oxide. It's a little bit cheaper than platinum and gold, and works as well as the gold. So another problem for this system is about cyclability. So here we have a cell where we can see the cyclability with the catalyst, and here without the catalyst. So we can see that the cycles start to lose capacity over the time here. And then when we see the number of cycles of this type of battery, we see about 30 to 50 cycles. So if you compare with lithium-ion batteries that are 3,000 cycles, 5,000 cycles, this system still has limited capacity in terms of cyclability and number of cycles. Today, we have like 100 cycles, 200 cycles, but we are still far away from 3,000 cycles. So the big like advantage of this battery, it has like long-term duration compared to lithium-ion batteries. So for example, imagine you charging your cell phone just once a week. This would be possible with lithium-air batteries. However, the number of cycles is really limited. So instead of 3,000 cycles, we have on the other, instead of 3,000 cycles, we have 300 cycles. So yeah, so how we improve this kind of battery? So if we understand the reaction mechanism, we can improve the capacity and cyclability. So this is the effort of a team in the last 6-7 years. So we have designed different kind of battery. So we could study these batteries with different techniques. So this battery here in 2018 is this bench cell, célula de bancada, where we can test the batteries. So inside the batteries, you have these layers of lithium metal, separator, cathode, and then we pressurize the cell with oxygen, and then we test the system. So to use different techniques, such as FTIR, X-rays, um, X-rays absorption, we change the cell design to try to do this analysis. So I'll show you some results that we have done in the last 7 years. We have a lot of help of Sirius. We submit different projects there. So Sirius is a fourth generation second source, and it's a really big microscope, and there we can understand the reaction mechanisms in an atomic or molecular level. So we have different ranges to study in the battery. We can study like the film that's formed in the surface of lithium peroxide. And we also can understand the particles that are formed there during the nucleation, such as the catalysts that we use in the process. So in lithium batteries, you can study three main areas. We can study the formation of lithium peroxide. We can study the electrolyte if it is stable during the cycles. And we also can study the catalyst and how it changes in the process. So talking about the formation of lithium peroxide, we can understand this mechanism. We can study the morphology of this lithium peroxide. Is this a big particle? Is this a small particle? Is this like a film that's formed under the cathode? We can also study the intermediates formed in the process. So to form lithium peroxide, we can have superoxide particles. We can have like lithium hydroxide in the process. Then we can understand better the reaction mechanisms. So this is one paper published in 2021 that studies the operando's cyclotron XRD, X-ray diffraction, of bromide-mediated lithium-oxygen batteries. So the idea is we study the lithium-oxygen battery using bromide as a redox mediator. So in the process, bromide is oxided, and it helps in the charge process of the battery. So here is one chart that shows the diffraction pattern here. So here's intensity, the degrees, and here's discharge and charge process. And then we can see the formation of lithium oxide, peroxide, and then the decomposition of lithium peroxide. So in this experiment, we could observe the formation and the composition, and then we validate our system that is forming this lithium peroxide. It was a really nice step in our group to see that our system was working well. So this is the experimental setup of this was not in Sirius, it was in the last accelerator. And then we can understand better the mechanisms here of the bromide and the formation of the peroxide. And then we also saw here the formation a little bit of lithium, I always forget this name, hydroxide. And then it's most because of a little bit of water in the system. So we need to avoid water as well. So this was a really nice experiment that we have done in 2021. So another way to understand batteries is to study the electrolyte. So one of the main electrolytes for lithium air batteries is DMSO. It's dimethyl sulfoxide. And then we could understand this electrolyte, how it works as well. So this is another study that uses infrared micro and nano spectroscopy in non-aqueous lithium cells. So in this case, we use a different type of cell with a golden surface here, really well polished. We have like a rugosity less than 50 nanometers here. And then we disperse carbon on the surface, and then we use like IR to understand this process. So IR is very sensitive to organic electrolytes. And in this case, we also could see like DMSO forming and decomposing, and you have some intermediates here forming the process. It was really useful to understand how the electrolyte works. This study was a cover of the magazine, the Advanced Journal, Advanced Iron Materials, and it's a really good journal. It's like impact factor 26 here in 2025. But I want to show you here that we took like 3 to 4 years to publish this paper. So I really want to encourage people here to do this kind of papers where we took really long time to do, because we have the different types of analysis being doing here, psychoanalysis, lab analysis. We also have simulation in this paper. So it really pays. So I want to encourage here students to do this kind of research, and don't worry if it's taking 2 or 3 years to publish, because it's really worth when you publish your paper here. So another area that you can study in lithium-ion batteries is about the catalyst. This is my field of research. So in this case, I study this spinel that's made of cobalt, manganese, and aluminum. Uh, this material was chosen from different kinds of materials, and it showed really high activity. So cobalt is a nice transition metal oxide to work. It has different oxidation states: cobalt +2, +3, cobalt 0. We also have manganese that has also different kind of oxidation states, and it's very active to decompose lithium peroxide. And we also have aluminum. Aluminum is really good for the structure of this spinel. It really maintains the stability, mechanical stability, and electrical stability of the spinel. So it's really nice to have aluminum in the structure as well. So in this process, when we study the catalyst, we can understand lithium intercalation in the catalyst. We can understand some structural deformation. We have here some kind of vacuums. And then I show you a little bit of the results that we haven't seen in the last years. So the first paper we published about this catalyst was a cell that has here lithium, the membrane, and the cathode with this spinel catalyst as catalyst. So it's made of cobalt, manganese, and aluminum, as I showed you. So here you have the carbon matrix. It was a carbon formed of um, carbon nanotubes. And here we can see the spinel particles. So when we test the cell, we have here in blue, the charge process, just using the carbon nanotube. And in red, we can see the carbon nanotube with the spinel catalyst. So you can see that kind of double the capacity of this battery. And we also reduce it. Are you guys seeing my cursor, my mouse?
Yes.
Nice. And then we have the decrease of the overpotentials as well. So here's the number of cycles, and we jumped from 10 cycles, just 10 cycles with using carbon nanotubes, to 40 cycles using the catalyst. And here we have some Raman spectroscopy when we can see lithium peroxide being formed. So here's before cycling, here's after cycling. We can see that form a film of lithium peroxide over the cathode. This window here is when we are doing like microscopy, and if we keep the beam in an area, we start to decompose the lithium peroxide that's really unstable. So here's the film formed of lithium peroxide over the cathode. Then once we published this paper, we were thinking, okay, but why? Why this catalyst is so active for the battery? Why this material is so powerful in lithium-oxygen batteries? Then we start to combine different techniques to try to understand why this catalyst is so active in lithium peroxide. How can we learn from it to redesign it or to engineer it to form a new catalyst that's really active? So we did a different kind of cathode here, so to understand this system, kind of simpler cathode. It's formed of carbon paper, that's just fibers of carbon, and then we impregnate these carbon fibers with particles of this cathode. So we made like transmission microscopy here to understand this material. And then we could see that have some shapes, different kind of shapes, like octahedron shapes. And in this shape of particle, we have some of surface that are exposed to the environment. So we could see that main these two surfaces, 111 and 100. And when we see papers, we see that the active uh, surface of this catalyst is the 111 surface. 100 is not that active. So we started to understand why this catalyst is active, and we start to study this 111 surface. So we did X-ray diffraction, and we could see that's really crystalline material. It's not amorphous. So although it has these three different kinds of cation, it's just one phase, that's the spinel phase, and it's really crystalline. We have performed some EXAFS analysis of this process. So EXAFS is a kind of absorption of X-ray experiment. And when we do that, we can see here um, like the distance between uh, atoms in angstroms. So we have here, like for example, the cobalt-oxygen bonds. The cobalt-oxygen bonds are these two. Here we have octahedral and tetrahedral cobalt. So we have this cobalt-oxygen and cobalt-oxygen bonds, and it's the first shell here. We also have the cobalt octahedral, cobalt octahedral distance here. We also have the cobalt octahedral to cobalt tetrahedral here. So we start to understand better this distance between atoms. And then we did the experiment. We could see here in black CO304, that's the commercial form of cobalt spinel, cobalt oxide. And then when we see the cobalt manganese aluminum oxide, that's material that we are working here, we see first here a decrease in the cobalt oxygen population. It indicates that we have oxygen vacancies in this material. So it's a really interesting result. So we can see that we have some defects in this material. And when we call defects, it's good for the material because when we have oxygen vacancies in this material, we have a really high energy surface. When we have a high energy surface, we can intermediate the formation and the composition of the lithium peroxide with this catalyst. So we also have some decrease here in the cobalt-cobalt bond. This is because we have different materials in this catalyst, such as manganese and aluminum, but we also have some defects in the cationic areas. So here's the experimental setup. We use this special cell that we use it. That's possible to use in transmission mode. So the beam like crosses all the cell here. This is another experiment we have done in this catalyst. That's microshunts by TXN. It's another X-ray absorption technique. So here we have the key edge of the cobalt. I will not explain this in deep, but here we can basically see the oxidation state of the cobalt. If it's cobalt 0, if it's cobalt +2, or if it's cobalt +3. So here we have three pictures. This is the texture of the catalyst. This is a agglomerate of cobalt particles, like here. Here's the concentration of the cobalt spinel. So we have agglomerate here, and we have just some particles dispersed. And here you see we have the oxidation state of the particles. So we could see the oxidation state of the particles over the cycle of discharge and charge of this battery. So this was an operando experiment. And the result is this. I will explain here a little bit. So in green, we have the first step of discharge of this battery, and then it goes to the yellow phase here, and then it goes back like to the red line here. So what happens in this catalyst is that when we have electrolyte here, in the presence of this battery, this cobalt manganese aluminum catalyst just absorbs some lithium and some oxygen from the atmosphere, and then it goes near to the cobalt zero oxidation states. So it's a mixture of cobalt zero and cobalt plus two oxidation state. So we have here cobalt plus one as an average of these oxidation states. Then when we start to discharge the catalyst, we start to form here lithium peroxide, and then the particles or the atoms or the ions that have been absorbed for the cobalt start to go out and form this really big film of lithium peroxide. Then when we start to the charge process, the lithium peroxide starts to decompose to the electrolyte, and then these particles continue to absorb these atoms, these ions, and then it goes back to the cobalt plus one oxidation state. So this catalyst works as a really big sponge, and it absorbs and gives catalyst to the electrolyte. So it works as nucleation centers for the lithium peroxide. That's why it increases the catalyst. So we are doing um, some computational simulation of this process with Pedro from Juarez group. Pedro is doing an amazing job in this process of simulating how the surface is and how the peroxide is formed here. So we have simulated here the 111 surface. That's the most active surface. Pedro has seen like, okay, if you have like oxygen vacuums, where can it be formed? So you have seen different possibilities here, and it's the most stable way to form these oxygen vacuums is here in the F place of this structure. So we have here the surface with this vacancy here, and then we have simulated the adsorption of an oxygen uh, molecule here. So it enters in this oxygen vacancy perfect as expected. So we also here see here the adsorption of a lithium ion here, and it goes as well here in the surface. Then another lithium exit ion, it also absorbs in this surface here, not near here. And then this absorption of oxygen, lithium goes on and on, and then we start to formate this lithium uh, cover over the cathode. And to finish like my presentation, I would like to show these last results that are still going on. I'm not an expert in this subject. It's X-ray inelastic spectroscopy. So here, scattering, sorry. So here you can see basically um, the D level of the cobalt atom for the doped material and then commercial material. And we can see that we have different energy states here. As I said, I'm not an expert in this in this process. If you have some student here that want me help to interpret, to understand these results, we just got the results like in the last 6 months. We are trying to understand these results. So we have different configurations of the d orbital of the cobalt in this case. And then we also perform some magnetic studies here to understand. We saw some hysteresis here for the doped material. So we're trying to marry these two results to make a paper to understand how this material is about the level of the cobalt. And to finish my presentation, I want to show you some next steps that we are trying to do in our lab. So we saw that we have the formation of this really thick film of lithium peroxide over the cathode. And of course, this limits the discharge process of the battery because lithium peroxide does not conduct electrons. So when we saturate the cathode with this material, the battery dies. So how can we overcome this process? So one of the ideas is to use lithium-oxygen redox flow batteries. So what's the idea here? We kind of circulate, so here's a pump that pumps the electrolyte into the battery here, and then it goes on and goes on between all the discharge process of the battery. So the idea here is when we circulate lithium, the electrolyte over in the battery, we kind of recover the, the lithium peroxide from the cathode, and then we free the active side to react again. So we can like get the peroxide out of the cathode during the discharge process, and then we decompose the peroxide in the charge process. So instead of forming the peroxide over the surface of the cathode, we start to form the peroxide in the solution here. So we have a tank um, in appendix to the battery, and it's interesting that the capacity is not proportional to the cathode surface, but it's proportional to the volume of electrolyte that I have here. So this is a really good possibility to be used in stationary state batteries, like together with solar power, together with wind power, because we don't need like big batteries stacks. We just need like big tanks where I can store this electrolyte, and we just use the battery as a surface to react and to form the lithium peroxide. So it's very flexible to be used in stationary energy. So I would like to thank you, like UNICAMP and CAPES and PQ, FAPESP for the funding, CINE Energy for all the structure, and also and Shell as well, and Sirius and SLAC for the collaboration, and also Juarez Group. It's not here in the slides, but has helped a lot with the simulation process. Thank you very much.
Okay, thank you very much, André, for the nice, insightful talk on the lithium-ion batteries, and they also provide some very deep details. Now we have time for questions. Okay, just raise your hand or write in the chat too. We start with Sara Barati.
Hi, Andrea. Thank you for your nice presentation. I like it. My question is about the capacity fade. You talk the most problem about this battery is capacity fade. What is the main reason or mechanism?
Actually, it's the other way around. The catalytic defect is very good for the battery because with catalytic defect, and when we say defect, it means you have some oxygen vacancies or some cationic vacancies that form a really high energy surface. And we like high energy surface because they are really good action sítios ativos, active sites for the formation and the composition of the lithium peroxide. So it's not a big problem. On the otherwise, it's a solution for good catalysts.
But excuse me, I didn't get about capacity fade. Why this battery capacity retain is not good? You talked after maybe 100 or 200 capacity fade a lot. Why?
Yes. So the main reasons for capacity decreasing is because lithium peroxide sometimes form another species that cannot be decomposed. For example, lithium carbonate, it's really stable, so it's really hard to decompose it. Another species, it's lithium hydroxide, that's hard to be decomposed as well. Another reason is because some of the lithium peroxide just goes to the solution and then we cannot access it to decompose it. And
I so based on your explanation, like lithium sulfur, we have deposition and shuttle, yes, in this
mhm.
battery.
Yes, I'm not an expert in lithium sulfur batteries, but I remember you have the shuttle effect.
Yes.
That's a big problem. It's kind of similar here for lithium peroxide.
Thank you. Excuse me, I have another question
Okay,
about.
excuse me, Sarah. Okay, we just round the questions one by one. Okay, otherwise is
Sure,
okay.
sure.
The next
But
question.
Sarah, if you want to talk more about this, we can email me
Okay, sure.
No,
or send me us, and we can exchange information, please.
Sure, sure.
Tapasendra.
Hello, Andre. Am I audible?
Hello.
Yeah, thanks for the insightful talk. So I have like question like in the slides you mentioned that for these lithium-ion batteries, like the H2O and CO2, these are detrimental, right? Like
Yeah.
so, and as in the slide also, like you have mentioned, these lithium-ion batteries take the air from the atmosphere, right? Like we don't use any specialized chamber. Like from the atmosphere, the it uses the oxygen, right? Like
Yes.
so
For
so how do we take care of the moisture, like if in used in commercial process, like there can be moisture in some places or the CO2, so how do we take care of that so that it the capacity fade doesn't happen or it doesn't become like lithium is explosive, right? So how do you take care? Can you please share your thoughts?
yes, thank you for your question. It's a really nice question. Well, so for laboratory tests, we just use pure oxygen. We don't use like atmosphere to do the tests. So it's easier for us because it's just experimental results. So for example, for this cell here that we have in the laboratory, we just pressurize it with oxygen, pure oxygen, no water, no CO2. To use these batteries with the ambient atmosphere, we need some membranes. There are some commercial membranes in the market. So these membranes are selective to the oxygen, so they don't allow CO2 and H2O to go to the cathode of the battery. So yeah, this is the solution, like these membranes. But this is another area of study. It's not our area of study here. We're not so worried about that. We just use like controlled environment. But in the future, if you want to have a commercial prototype, we need to think about that. You are right.
Thank you, Andrew.
Okay, some additional question in case don't have. Okay, Sarah, if you want to have additional question now, you are free, or you make a question. Okay.
Professor Tapasendra asked my question.
Okay, understand. Good. Okay, I have one question just before the next question. And from my understanding, for example, when you combine the experimental and the computational work, how the computational simulations would help you to explain your data? I mean, how much was important this part of the work?
Perfect. Thank you for your question. Professor. Well, in this case, we have simulated like surface such as graphene surface that could be like near to the carbon surface we have. And then we also simulated the cobalt spinel surface. And we saw that the adsorption of lithium and oxygen over the cobalt surface, it's higher, like 4 times, 8 times higher than in the carbon. So this is a good results that match the result that we have experimentally, that we saw that the cobalt is a big sponge for the lithium and for the oxygen. So this is one of the results. And another result is the confirmation of the mechanism of formation of lithium peroxide. So we could see that the adsorption it's preferential in the vacants of the oxygen. So this is a nice result. And the reaction starts there. So the cobalt is a reaction site, a nucleation site for the peroxide in the system. So these are the two main results that we could understand.
Okay, good. Okay, we have one additional question by Tapasandra.
Hey, Andre, thanks once more. So I have two questions, like one from Raman and the second from XRT. So from the Raman, like you showed us the like a Raman spectra curve. So like as we can see, like can you please go in the Raman? Then I can.
I will find it here.
Yeah. I think here, yeah. So you have shown in the Raman spectra the green one is for pristine and the black one means after like you have cycled you have so as we can see like DMSO the electrolyte which you have used like after cycling the peaks are small, so does it mean that it decomposed like while we use in the batteries as an electrolyte, like does it, like the peaks are small, so like since air is there like O2 oxygen is there, so does it have the possibility to like decompose and the capacity fade happens due to that? So can you please?
Sure, thank you for your question. It's a good point. So actually, we have studied the catalyst over cycles, and we saw that it doesn't decompose. It doesn't break, it doesn't change phase. So what happened here, actually, it's more about the morphology of the cathode. As you can see here, the cathode has a thick layer of lithium peroxide. So we cannot access the cobalt phase here. So basically here in the surface, we can just see the DMSO, some resquício from the tests. And here we have most lithium peroxide in the surface. So it's more about the morphology of the cathode after discharge and not about the decomposition of the catalyst. But it's a nice insight. Thank you for the question.
Thank you for the explanation. And so another question is from the XRD. Like, can you explain a little bit more, like about what material the XRD peak is about? Just up top, the XRD above this, I think the previous slide.
The previous one?
Yeah, there was some XRD peaks, like one with the reference, and you put some X-ray diffraction peaks. Can you go back, like?
Sorry.
This one. Yeah, this.
Okay. Yes. So this is X-ray diffraction, actually. So each plane here is a plane of this cobalt structure here. So, for example, this could be 111, this could be 311, this could be 011. I'm not sure if you are familiar with the technique. So each plane here, it's like one plane for the cobalt oxide spinel. And then here's the experimental result. So here is a pattern that you have in literature. It's a PDF, we call it, and shows the position of the peak and the height of the peak. And then we compare it with the experimental results. Then we could see that we have a really crystalline phase, not amorphous, and in the spinel phase. It's not another phase.
Okay. Thanks.
Thank you for your question.
Okay, thanks for all the questions. Okay, let's thank the speaker once again. Okay, for his nice and insightful talk on the topic of lithium-ion batteries, and then we see everyone again. Okay, just before we left, I just recommend you just invite your colleagues to take part in these CINE Talks. It's a great opportunity for everyone to learn a different topic and to build up a more multidisciplinary environment, which is necessary for a lot of high-level, high-impact journals nowadays. Okay, thanks a lot. Have a nice day. Bye. Nice weekend too.
Thank you.
Thanks.
Bye-bye.